Hello there, and welcome to The Sleepy Scientist. If you're new here, I make calm, curiosity-driven explorations into the wonders of science, designed to help you drift off a little more curious than you were before. And if you've been here before, welcome back, dreamy voyager. It's good to see you again. Tonight, we're going to float gently beyond Earth's atmosphere, into a realm where up and down lose their meaning, and the ground is, well, optional. We're headed into space, not for the thrill of rockets or the buzz of launch control, but to explore something deeper, quieter, and far more mysterious. Gravity. It's the force that keeps your feet on the floor. The reason your tea doesn't float off the table. The silent sculptor of stars, galaxies, and that unfortunate moment when your toast lands jam side down. But what if you could step away from it, just a little, and see what the universe feels like without gravity constantly tugging at your sleeves? In this video, we're going to explore what floating in a vacuum really teaches us about gravity, what happens to astronauts in orbit, how gravity shapes our bodies and minds, and how Einstein turned the whole concept upside down, all in a way that's light, gentle, and hopefully sleep-friendly. Now, I should probably warn you, this video is dangerously informative. I'll do my best not to make it too interesting, but if you find yourself staying awake pondering the warping of space-time, well, at least you'll be learning something. That's a pretty good trade-off for a few lost zizzes. Before we launch though, I'd love to ask you a small favor. If you enjoy tonight's trip through the cosmos, consider giving this video a like and maybe subscribing to The Sleepy Scientist. It really helps more wandering minds find their way here. And if you feel like sharing, let me know in the comments. Where in the world are you watching from, and what time is it right now? There's something oddly comforting about imagining people all across the planet, Sydney to Stockholm, midnight to morning, settling in with a cup of tea, or sliding under the covers, all connected by a shared curiosity and a love of soft science and quiet stories. Now, wherever you are, I hope you're comfy. Maybe you've dimmed the lights, fluffed your pillows, or turned on a star projector. Maybe your cat is already snoring. Wherever and however you're listening, I invite you to let your body relax, your breath slow, and your mind wander just a little. We're not in a hurry here, we're just floating. Because in space there's no up, no down, only motion, curves, and quiet. Astronauts describe the feeling of microgravity as both liberating and disorienting. You can flip and twist and float in place. A simple push sends you gliding across a room, and yet everything around you is still very much under the influence of gravity. It just doesn't feel like it. That's the trick we're going to explore tonight. What seems like weightlessness isn't the absence of gravity, it's the presence of something stranger. Perpetual fall, perfect motion, and a kind of cosmic sleight of hand. And to understand that, we'll have to visit not just the International Space Station, but the minds of Newton and Einstein, the pull of black holes, and the peculiar effects gravity has on the human body. But we'll go slowly. This isn't a rocket launch. It's a slow drift out of Earth's atmosphere and into the invisible web that binds the universe together. So take one last look at the surface beneath you, wherever you're lying or sitting. Feel the gravity holding you down, like a gentle hand on your back. It's been with you since the moment you were born. But for the next little while, we're going to imagine what it feels like to loosen that grip, to float beyond it, and to see what secrets gravity has been hiding from us all along. Because sometimes the best way to understand something is to leave it behind for a bit. All right, sleepy scientists, let's begin our journey. Floating in a vacuum, what space teaches us about gravity? So, what is gravity? It's one of those questions that seems simple, until you actually try to answer it. You might say, well, it's what pulls things down. And that's not wrong, but it's a bit like saying sleep is what happens when you close your eyes. True, but there's so much more going on. Let's start at the beginning. Not the Big Bang beginning. We're easing into this. Let's just rewind to an apple falling on Sir Isaac Newton's head. Except, spoiler alert, the apple didn't actually hit him. At least not according to most historians. But it did get him thinking. Back in the late 1600s, Newton proposed that gravity was a force, an invisible tug that objects with mass exert on one another. You, me, the moon, your dog, we all pull on each other just a tiny bit. The Earth, being big and round and full of itself, pulls a lot harder. That's why you fall down, not sideways when you trip. According to Newton's laws, the more mass something has, the stronger its pull, and the closer you are, the stronger the effect. That's why the Sun keeps the planets in orbit. It's massive, and we're relatively close. Not hugging distance close, thankfully. Just a comfortable 93 million miles. Newton's model was brilliant. It let us predict how apples fall, how planets orbit, and how to shoot cannonballs farther than your neighbour. It held up for over 200 years. But then along came Einstein, with that twinkle in his eye and a fondness for turning things inside out. In 1915, Einstein published his theory of general relativity, a beautifully mind-bending idea that reimagined gravity not as a force, but as a kind of curvature in space and time. Imagine the universe as a stretchy fabric. Place a bowling ball on it, say the sun, and it creates a dent. Roll a marble nearby, like Earth, and the marble will spiral inward, not because it's being pulled, but because it's following the curves in the fabric. In other words, gravity isn't something the sun does to Earth. It's simply the way Earth moves through the curved space-time the sun creates. Planets aren't being yanked. They're just following the straightest possible path through a very bendy universe. Now, this is the part of the script where your pillow might start to feel unusually heavy. That's okay. Let your thoughts float, even if the space-time around you doesn't. So, Newton said gravity is a force. Einstein said it's a feature of geometry, and both are right in their own ways. Newton's equations work beautifully for everyday things: cars, satellites, falling toast. Einstein's model kicks in when things get weird: black holes, light bending around stars, or the slight slowing of time on GPS satellites. Yes, you heard that right. Time ticks differently in stronger gravitational fields. This has been measured. Your head experiences time slightly faster than your feet. Not enough for you to time travel or anything, just enough to make physicists very excited and GPS engineers very nervous. If this is all starting to sound like science fiction, I promise, we're still in the realm of established science. Gravity affects space, time, light, and even your sense of direction. It's why astronauts on the International Space Station feel weightless, not because gravity is gone, but because they're in constant free fall. They're falling around the Earth, not into it, like being stuck on a roller coaster loop that never ends. But gravity isn't just about falling, it's about order. Without it, stars wouldn't form, planets wouldn't orbit, you wouldn't stay on your chair. Even your body, your bones, muscles, fluids, are shaped by gravity's constant whisper. In fact, gravity is so deeply woven into our lives that we barely notice it until it's gone. That's when things get strange. Your spine stretches, your balance falters, your fluids start drifting, and your brain, bless it, tries to make sense of a world that no longer has a down. We'll get to all of that soon. For now, just let this idea settle gently in your mind. Gravity isn't just something that pulls. It's the quiet choreography of the cosmos. It tells things how to move, when to stop, and where to orbit. It governs tides and seasons, moons and galaxies, and yet it never makes a sound. It's the softest of rulers, and perhaps the most essential. So the next time you feel your body sink into your mattress, remember, that's gravity, holding you close. Not with force, not with flair, just with quiet, universal persistence. And if you're still awake, don't worry. There's plenty more wonder to come. In the next chapter, we'll leave the abstract behind and step into the world of astronauts, where floating feels like flying, but gravity still lurks behind every twist and turn. Let's float on. So you're in space. You've made it past the atmosphere, left Earth's gravity tugging below, and now you're floating, arms outstretched. A little spin, a little tumble. Maybe a pen drifts past your nose in slow motion. It feels like magic. But here's the curious thing. You're not actually weightless. Wait, what? That's right. Despite how it feels, gravity hasn't let go of you. In fact, even on the International Space Station, roughly 400 kilometers above Earth, gravity is still about 90% as strong as it is on the surface. The reason astronauts float isn't because gravity is gone. It's because they're in a state of continuous freefall. Let's explain that in the sleepiest way possible. Imagine you're on a very tall roller coaster, so tall it scrapes the edge of space. At the very top, the car disconnects, and instead of falling straight down, it moves forward so fast, around 28,000 kilometers per hour, that as it falls, the curve of the Earth drops away beneath it at just the same rate. You fall, and fall, and fall, but never hit the ground. You're not hovering, you're orbiting. That's what astronauts are doing. They're falling sideways, fast enough to miss the Earth entirely, and they've been doing it since the moment the rocket dropped them into orbit. So when we say zero gravity, what we really mean is microgravity. It's not the absence of gravity, it's the experience of weightlessness while under gravity's influence. A helpful analogy. Imagine being in an elevator. A very unlucky elevator. The cables snap and it begins to fall. For a few terrifying seconds, everything inside seems to float. The apple you were holding, your cup of tea, even you yourself, everything drifts beside you. You haven't escaped gravity, you're just falling at the same rate, so nothing pushes back against your weight. That's what's happening on the ISS, except without the terror and with far better snacks. Astronauts live and work in this state for months at a time. And while it looks like fun, you've probably seen them flipping around and chasing floating M&Ms, there are all kinds of strange consequences. For one thing, your inner ear gets confused. It relies on gravity to tell you which way is up, and when that signal vanishes, your brain says, well, this is a weird dream. Nausea is common at first. So is bumping into things. In microgravity, Newton's laws come alive. Every action has an equal and opposite reaction. If you push off a wall, you will go flying across the module, possibly into someone else's floating lunch. Even the simplest tasks become an exercise in adaptation. Imagine brushing your teeth, but the toothpaste tries to escape, or using a bathroom without the benefit of things, staying where they should. Astronauts have to learn how to move, sleep, and eat all over again, as if Earth had never trained them. And speaking of sleeping, astronauts don't need pillows. Or beds, really. They float inside sleeping bags tethered to the wall. No tossing or turning, just drifting, gently, in a private cocoon of silence. Some say it's the best sleep they've ever had. Others, not so much. In microgravity, your body becomes a new experiment. Fluids redistribute without the downward pull of gravity, so your face can puff up, your legs can shrink a little, and your sinuses might feel permanently congested. The technical term is space face. It's not as glamorous as it sounds. Over time, bones begin to lose density. Muscles weaken. Without gravity pushing against you, your body no longer needs to resist that constant downward force. So it doesn't. Which is why astronauts exercise for 2 hours a day, just to keep their Earth-strength muscles and bones from going soft. Even your spine stretches. Some astronauts grow up to 2 inches taller while in orbit. Of course, they shrink back down when they return to Earth, but it's a nice temporary perk, unless you already barely fit in your seat. But perhaps the most intriguing thing about microgravity isn't what it does to the body. It's what it teaches us about how deeply gravity shapes everything we do. Here on Earth, we take it for granted that objects fall, that water pours downward, that food stays on the plate, and your chair stays on the floor. In space, all of that changes. The rules are rewritten. Water forms floating blobs that cling to surfaces and float like little jellyfish. Food must be sealed, sticky, or squishy, lest it become a choking hazard mid-air. You don't walk anywhere. You pull yourself, hand over hand, through the modules. There's no down. There's only where your feet are tethered. Astronauts often describe their first days in orbit as disorienting, physically and psychologically. But over time, their brains adapt. New habits form. Microgravity becomes the new normal. And when they return home, that's when things get weird all over again. Astronauts have been known to forget they can't let go of objects. They drop tools, trip over their own feet. Some instinctively let go of a pen and expect it to hover. One cosmonaut said he almost floated out of bed trying to turn over. So when we say floating in space is weightless, it's more accurate to say your body feels weightless, but gravity never left the room. It's still pulling, just not in a way your senses are used to. And in that gentle confusion lies a kind of beauty. Because it reminds us that gravity isn't just something we deal with, it's something we've built our entire existence around. Our muscles, our bones, our habits, our inventions. Take it away, even briefly, and the world becomes a quiet dream of motion, softness, and strange new rules. A place where floating feels like flying. And yet, gravity is still there, quietly guiding you, always pulling, even when you no longer feel it. In the next chapter, we'll go deeper into life aboard the International Space Station. How do astronauts eat, clean, work, and live in this floating world? And what ingenious solutions have engineers invented for a place where everything, including the crumbs, tries to escape? We've left gravity's tug behind, learned how floating isn't true weightlessness, and now we find ourselves somewhere truly strange. Inside the International Space Station, a laboratory, a spacecraft, and for 6 people at a time, a floating home circling the Earth every 90 minutes. From the outside, the ISS looks a bit like a high-tech tin can with solar wings. But inside, it's a carefully engineered ballet of floating bodies, gently blinking machines, and the hum of recycled air. It's not glamorous, but it is quietly extraordinary. So, how do you live in microgravity without everything flying into chaos? Let's start with eating. On Earth, eating is easy. Gravity does the heavy lifting, keeping food on your plate, your drink in the cup, and your soup in the bowl. In space, none of that works. Liquids float, food crumbles, and rogue bits of tortilla can become deadly if they drift into a ventilation fan. That's why astronaut food is different. Meals come in sealed pouches, Drinks are sipped through straws with clamps, and spoons are magnetic, or velcroed, or strapped down somehow, because losing your cutlery mid-meal is surprisingly easy when it doesn't stay put. Fun fact, tortillas are preferred over bread in space. Why? Because they don't produce crumbs. Crumbs float, and floating crumbs can end up in your nose, your eyes, or worse, inside critical electrical panels. In microgravity, a wayward cornflake is basically a villain. Now imagine sleeping. In space, you don't lie down. There's no down. So astronauts sleep inside small, phone booth-sized cabins. They zip themselves into sleeping bags that are tethered to the wall, ceiling, or any other surface that feels cozy. There's no pressure on your back, no weight on your joints, just floating. Most astronauts say it's like being wrapped in a soft cloud. No tossing, no turning, just a kind of gentle suspension. Though occasionally someone forgets to zip in properly and floats around like a wayward balloon until they bump into something. Sleepwalking is complicated when there's no floor. Then there's personal hygiene. Baths? Nope. Showers? Not quite. Water doesn't fall in space, so you can't stand under it. Instead, astronauts use rinseless wipes and no-rinse shampoo. To wash, you squeeze out a blob of water from a pouch, catch it, and rub it around your face or arms. The water clings like a jelly bubble. It's more of a sponge bath, floating style. Toilets, by the way, deserve their own award. There's no gravity to, well, help things along, so space toilets use airflow, a vacuum system that pulls waste away. Everything must be very precisely aimed. Astronauts use foot straps, thigh harnesses, and careful training. Yes, there is a manual. Yes, they practice. And yes, it's awkward. Urine is filtered and recycled into drinking water. Yep. Today's coffee is yesterday's tea. NASA has a slogan. Yesterday's pee is tomorrow's Gatorade. It's not just resourceful, it's vital. Water is heavy to launch, so every drop counts. How about getting around? Astronauts don't walk, they float. To move, they push off with their hands and glide gracefully through the narrow modules. At least that's the idea. In reality, it's more like controlled ricocheting, bumping into walls, twisting mid-air, missing the handrail and doing a slow, awkward spin while trying to regain control. To stay put, they use foot loops, handrails, and Velcro. So much Velcro. Everything is labelled and stuck down. Clipboards float, pens float, laptops float. You don't place something down, you attach it, or it floats off like a stubborn balloon. Now let's talk daily routines. Astronauts work around 12 hours a day, 6 days a week. Their time is scheduled down to the minute. Science experiments, maintenance, repairs, comms with ground control, plus exercise. Remember, in microgravity, bones and muscles weaken quickly. To counter this, astronauts must work out for about 2 hours a day. That includes treadmill running, with bungee cords to simulate body weight, resistance training, and cycling. There's even a space gym. It's small, a bit noisy, and looks more like a medieval torture device than a place for wellness, but it keeps astronauts fit and grounded, metaphorically speaking. After work, they can relax. They watch movies, video call their families, read, or look out the window. Specifically, the cupola. The cupola is a 7-windowed observation dome offering stunning views of Earth. Imagine seeing sunrises and sunsets every 45 minutes. Lightning storms from above. Cities glowing softly in the night. The thin blue line of our atmosphere, fragile and beautiful. It's enough to make even the most seasoned astronaut stop and stare. Many say it's the most peaceful place on the station, a kind of sacred corner, a reminder of why they're up there in the first place. But despite the wonder, space life isn't easy. It's cramped, it's noisy, constant fans, pumps and beeps. There's little privacy. You share a bathroom with 5 other people. You float into each other's personal space. A lot. And the food? Well, let's just say you don't go to orbit for the cuisine. Still, most astronauts describe the experience as transformative, not just because of the view or the science, but because of what it teaches you about life back on Earth. Things like water, privacy, gravity, and fresh air. Things we often take for granted become precious in space. Every drop matters. Every breath is a gift of engineering. And the sight of our pale blue dot, fragile and alone in the vast blackness, can shift something deep inside. Living in microgravity isn't just a technical challenge. It's a lesson in perspective, in adaptability, in humility. Floating, it turns out, teaches us a lot about being human. In our next chapter, we'll explore what happens to the human body in space. Not just the temporary puffiness and stretched spines, but the deeper biological effects. How gravity has shaped our evolution, and what happens when we live without it for too long. So take a deep breath. Let your limbs relax. You're still grounded, but just for a moment, imagine the quiet hum of a floating lab, the Earth spinning slowly below, and the wonder of life in orbit. So far, space sounds kind of dreamy, doesn't it? No gravity, no rushing. You float from task to task like an underwater ballerina. The Earth glows below like a nightlight for the galaxy. And your hair? Always effortlessly voluminous. But for all its wonder, space has a quiet cost. And tonight, we're going to explore what microgravity really does to the human body. The strange shifts, the surprising challenges, and the hidden ways gravity has been shaping us all along. Because here's the secret. Your body loves gravity. It's used to it. It's been dancing with it since the moment you were born. Gravity tells your muscles when to flex, your bones how to grow, your blood where to go. Without that constant invisible pull, your body starts to ask, wait, what are we doing? Let's start with something subtle. Fluid shift. On Earth, gravity pulls bodily fluids, blood, water, lymph, downward. That's why your feet swell when you stand too long, and why your sinuses feel clear when you lie down. But in space, with no down, fluids redistribute. They move upward. Your face becomes puffy. Your legs, strangely skinny. Astronauts often call this the Charlie Brown effect. Big head, small legs. Your sinuses fill up, your voice changes, and your body starts to look like it's wearing an invisible pressure suit, backward. This fluid shift also affects your eyes. Something called SANS, spaceflight-associated neuroocular syndrome, can cause pressure to build up behind the eyes, flattening the eyeball slightly and affecting vision. Some astronauts return to Earth with lasting changes in eyesight. Not ideal when your job involves reading checklists and not floating into walls. And speaking of walls, your bones and muscles aren't doing much up here. On Earth, even standing still is a workout. Your legs bear weight. Your back holds you up. Your skeleton responds to that pressure by staying strong. But in space, no weight, no pressure. So your bones begin to weaken. In fact, astronauts lose about 1% to 2% of their bone density per month in orbit. That's like aging 10 years, in just a few months. The hips and lower spine are especially vulnerable. Calcium leaches out of the bones, and it doesn't always come back fully when you return to Earth. Muscles suffer too. The big ones, your quads, calves, back, shrink quickly without daily effort. That's why astronauts have such rigorous workout routines. 2 hours a day, 6 days a week. It's not about vanity, it's survival. Without exercise, returning to Earth would be like trying to run a marathon after lying in bed for a month. Even your heart gets a little lazy. In microgravity, it doesn't have to fight to pump blood upward. The workload drops. The heart can shrink slightly. When astronauts come back, they sometimes feel lightheaded or dizzy because their cardiovascular system has forgotten how to deal with gravity. Your vestibular system, the part of your inner ear that controls balance, gets confused too. It uses gravity to tell which way is up, so in orbit, it basically throws its hands in the air and says, "You're on your own." That's one reason astronauts often experience space motion sickness during their first days in orbit. Headaches, dizziness, nausea. Not exactly the glamorous life of a sci-fi hero. And then there's your spine. Without the compressive force of gravity, the vertebrae in your back relax and separate slightly. This causes astronauts to grow up to 2 inches taller in space. It sounds great until you remember they're in a metal tube designed for people 6 inches shorter. Getting wedged in your sleeping bag isn't quite as majestic as it sounds, but the biological changes aren't all bad. Living in space has helped us understand how gravity shapes everything about human development. It's taught us that bones don't just form, they respond. Muscles don't just grow, they adapt. Even our cells behave differently in orbit, with changes in gene expression, immune response, and how wounds heal. Space in many ways is the ultimate laboratory, and it's not just about astronauts. These lessons come back to Earth. The research done in microgravity helps doctors understand osteoporosis, muscle atrophy, fluid balance disorders, and more. Space medicine is helping Earth medicine, one floating guinea pig at a time. But let's not forget the psychological side of space. Living in a confined space, away from family, on a strict schedule, with only 6 other people, and nowhere to go. It takes a toll. Astronauts deal with isolation, disrupted circadian rhythms, and the strange emotional weight of looking down at their entire world. To cope, they stay connected to loved ones, follow carefully designed routines, and find meaning in their work. They take photos, read books, play instruments, and yes, watch movies. Popcorn is sadly banned, but digital comfort is still possible. The longer we stay in space, the more we learn. Humans are deeply tied to gravity. It's part of who we are. Take it away, and we begin to unravel, slowly, silently, and with surprising grace. But we also learn how resilient we are, how adaptable, how brilliant we can be in the face of unnatural conditions. Floating in space may be strange, but it shows us just how incredible our Earth bodies really are. In the next chapter, we'll shift our focus from biology to technology, because to survive and thrive in orbit, we don't just need muscles, we need machines. From toilets to airlocks, spacewalk suits to solar panels, we'll explore the ingenious designs that make life in orbit possible, and the quiet ways gravity shapes every engineering decision. For now, breathe deeply, feel the steady pressure of your bed, your blanket, the air around you. That's gravity, reminding you you're home. Let's take a moment to appreciate something that rarely gets the spotlight in bedtime stories. Space engineering. It doesn't sparkle, it doesn't float, it doesn't even look particularly sleek. No chrome fins or warp drives here. But it's the reason astronauts don't freeze, starve, or spin endlessly into the void. And at the heart of all this quiet, life-sustaining brilliance is a familiar, invisible force. Gravity. Tonight we're going to explore how gravity, the thing space seems to lack, still shapes nearly everything about how we build for it. From spacecraft design to astronaut gear, from life support systems to the humble space toilet, gravity is the invisible engineer whispering in the background. Let's start with something simple: launching. To get into space, you first have to escape gravity's grip. That takes an astonishing amount of energy. Earth's gravity isn't messing around. To break free, you need to hit escape velocity, about 11.2 kilometers per second, or roughly 33 times the speed of sound. That's why rockets are essentially controlled explosions wearing pointy hats. The sheer amount of fuel needed just to get a modest payload into low Earth orbit is staggering. In fact, most of what you see when you look at a rocket isn't cargo or crew, it's fuel tanks. Enormous, elegant towers of propellant built to push against the strongest, most constant force we know, Earth's gravitational pull. And once you're up there, gravity doesn't leave you alone. It just changes roles. Now, instead of resisting gravity, your spacecraft must work with it, stay in orbit, balance speed and altitude, avoid re-entry, and adjust position without falling out of the sky or floating into deep space. Even the shape of a spacecraft is determined by gravity. Capsules like those from Apollo or SpaceX aren't pointy for fun. Their blunt body design helps them survive re-entry, using the atmosphere and gravitational pull to slow down, create drag, and distribute heat. Gravity becomes the final boss at the end of every mission, a test of engineering, physics, and sheer material strength. Now let's head inside the spacecraft, where things get more delicate. In microgravity, every movement matters. There's no friction to naturally slow things down. If you twist a valve too hard, it might float away. If you open a bag too fast, its contents will scatter like glitter at a toddler's birthday party. So engineers have to design every tool, button, panel, and drawer to work without gravity. That means Velcro on everything. Bungee cords for storage. Foot loops and handrails so astronauts can anchor themselves. Color coding, labels, and tactile differences so people can find things quickly in a disorienting environment where up doesn't exist. Even your average drink pouch has to be an engineering masterpiece. Regular cups don't work, pouring doesn't work, so fluids are stored in vacuum-sealed bags, sipped through special straws with clamps. It's like drinking a juice box designed by NASA, which essentially it is. Now, let's talk about air. You don't really think about air until it's gone. In space, you need to bring your own and keep it circulating, filtering, and pressurizing 24/7. Earth's gravity helps move air naturally. Warm air rises, cool air sinks. In orbit, no such luck. Air doesn't flow, it stagnates. So space engineers design complex ventilation systems with fans and ducts to keep oxygen moving, carbon dioxide out, and smells manageable. Because yes, space can smell. More on that later. Even more impressive is the life support system. These machines maintain the temperature, humidity, and oxygen levels, all while filtering out trace gases and microbial growth. It's like living inside a high-tech aquarium, except the fish have laptops and treadmills. Speaking of treadmills, exercise equipment must be gravity independent too. On Earth, a treadmill works because you're pulled down into the belt. In space? Not so much. Astronauts have to strap themselves down with bungee harnesses, simulating the feeling of body weight. Resistance machines use vacuum cylinders or flywheels to mimic gravity's pull. And it works. These devices are crucial to preventing bone loss and muscle atrophy. Without them, astronauts would come home weaker than overcooked spaghetti. Now, the part you've secretly been waiting for: toilets. Ah yes, the most famous unsung hero of space engineering. In microgravity, traditional plumbing doesn't work. Water, and well, everything else, floats. So toilets use vacuum suction to pull waste away. Astronauts must aim very carefully, strap in tightly, and follow very specific instructions. Urine is filtered, purified, and recycled into drinking water, a process that's ickier in theory than in practice. NASA's motto, "Yesterday's coffee is tomorrow's coffee." It's all part of the closed-loop system that keeps life sustainable in orbit. Waste that can't be recycled is sealed in bags and stored until it can be incinerated during re-entry. Yes, some things literally burn up in the atmosphere, which feels strangely poetic. Even the spacesuit, that iconic white marshmallow armor, is a marvel of gravity-aware design. On Earth, a suit might weigh 300 pounds. In orbit, that weight vanishes, but the mass remains. If an astronaut pushes off too hard, they could go spinning. Every inch of the suit is engineered to provide mobility, pressure, oxygen, communication, and thermal protection, while still allowing the astronaut to move, grip tools, and not float away. And what happens if they do float away? They have a backup system called SAFER, a kind of mini jetpack that lets astronauts maneuver back to safety with gentle puffs of nitrogen gas. Not dramatic, not flashy, just a calm return to where they're meant to be. Like the space version of finding your way home after drifting off at a party. So yes, even though space is defined by the absence of gravity, our entire approach to it is built around grappling with gravity's memory. We launch to escape it, design to defy it, build to replace it, and always, always, we feel its influence. In fact, when astronauts return home, gravity hits hard, literally. They often collapse under their own weight, stumble as their blood pools in their legs again, or feel faint as their heart relearns how to pump against pressure. One astronaut described it as re-entering a world that suddenly feels 10 times heavier. Another said the strangest thing was having to hold their arms up again, because they'd forgotten what it felt like for them to have weight. Gravity isn't gone in space. It's just hiding, quietly influencing every movement, every calculation, every breath. The silent engineer, ever present, even when it seems to vanish. In our next chapter, we'll take a step back, way back, and look at the cosmos itself. From the birth of stars to the formation of galaxies, gravity doesn't just pull, it creates, it sculpts, it shapes the very structure of the universe. So let your mind drift outward now, beyond the station, beyond the moon, beyond the solar system. Because gravity's reach is infinite, and so is its story. By now, we've seen how gravity shapes life, engineering, and even our ability to brush our teeth in orbit. But we've only been looking at the local effects: human scale, Earth scale, station scale. To really understand gravity, we need to zoom out. Because out there, in the vast reaches of space, gravity isn't just a force. It's a sculptor, shaping the very architecture of the universe. Carving stars, sculpting galaxies, orchestrating the dance of cosmic structures too vast for us to fully grasp. Let's start small, astronomically speaking, with a nebula. A nebula is a cloud of gas and dust floating in space. Alone, the particles drift peacefully. But then gravity steps in. Ever so gently, it begins to pull particles together. A few clump, then a few more. As mass accumulates, the gravitational pull grows stronger. Eventually, the pressure at the core becomes intense enough to ignite nuclear fusion. A star is born. All thanks to gravity, slowly nudging hydrogen atoms closer until they burst into light. This is how our sun formed. and how every other star you see in the night sky began its luminous life, condensed from a dust cloud by the quiet insistence of gravity, not with a bang, but with a gradual tightening, like the universe drawing a breath. Now scale up. These stars don't form alone. They tend to gather in clusters, swirling together under mutual gravitational attraction. Over time, these clusters gather more mass. They orbit one another, and eventually they become part of something far grander, a galaxy. Galaxies are gravity's most elegant creations. Our own, the Milky Way, contains an estimated 100 to 400 billion stars. Spiral arms of gas, dust, and stellar nurseries twist around a central bulge, bound together by gravity like dancers circling a cosmic ballroom. The stars are moving at incredible speeds, yet they don't fly apart. Why? Because gravity keeps them tethered, each star responding not only to its neighbours, but to the unseen mass at the heart of the galaxy. That includes not just stars and dust, but something more mysterious: dark matter. We can't see it, we can't touch it, but we know it's there because galaxies rotate too fast for their visible mass to hold them together. Without some extra gravitational glue, they'd fly apart like leaves in a storm. Dark matter, whatever it is, exerts gravity, and that gravity keeps galaxies intact. And the Milky Way, it's not alone. It's just one of hundreds of billions of galaxies scattered across the universe like glowing islands on a dark ocean. They cluster into groups, then into superclusters, forming a vast web-like structure on the cosmic scale. It's called the cosmic web, and it's beautiful. Thread-like filaments of galaxies stretch across unimaginable distances, intersecting at dense nodes where clusters reside. These structures aren't random. They've been shaped by billions of years of gravitational interaction, mass pulling on mass, forming patterns as old as time. But gravity doesn't just hold things together. It can also warp them. One of the most astonishing predictions of Einstein's general relativity is that massive objects don't just attract, they bend space and time around them. This bending can cause light itself to curve. It's called gravitational lensing. Imagine a distant galaxy behind a massive cluster. The light from that faraway galaxy doesn't travel in a straight line. It bends as it moves through the warped space-time caused by the cluster's mass. To us, the galaxy appears stretched, magnified, sometimes even duplicated. We've used gravitational lensing to detect galaxies too faint to see directly and to map dark matter, which reveals itself only through the way it bends light. In this way, gravity becomes not just a sculptor, but a telescope. And then there are the extremes. Black holes, the end result of massive stars that collapse under their own gravity, so dense that not even light can escape. They're not cosmic vacuum cleaners. They don't suck everything in. But their gravity is so intense, their effects ripple far beyond their event horizons. Black holes bend light, twist time, and generate some of the most energetic events in the known universe. Entire stars can be shredded if they wander too close. And yet these terrifying objects are also essential. At the center of nearly every galaxy, including ours, lies a supermassive black hole, millions or billions of times the mass of our Sun. We're not sure how they formed, but their gravity anchors their galaxies. Without them, the graceful spirals we see might never have held together. So from dust clouds to starbursts, from spirals to clusters, from lensed galaxies to hidden giants, gravity is the architect of it all. And it doesn't work quickly. Gravity plays the long game. It's the quiet artist, taking billions of years to craft a galaxy, billions more to guide stars in their orbital paths, and still longer to build the great cosmic web that spans the universe. It doesn't shout, it doesn't hurry, it just shapes. And yet, for all we understand, there's so much we don't. We can describe gravity, we can observe it, measure it, predict its effects. But ask a physicist what gravity is, in its deepest sense, and you'll get a shrug, followed by a lecture. Some think gravity may not even be a fundamental force, that it could emerge from something deeper, some hidden feature of quantum reality we haven't uncovered yet. We'll touch on that mystery soon. For now, remember this. When you look up at the stars, you're seeing gravity at work. Each point of light was born from it, shaped by it, held in orbit by it. Even the photons that reach your eyes were nudged, bent, and guided by it. In every direction, across every distance, gravity leaves its mark. We've been describing gravity as a force for most of this journey, a kind of invisible tether holding apples, astronauts, and galaxies in place. But then Einstein came along and rewrote the rules. In 1915, with a twinkle in his eye and hair that obeyed no force known to man, Albert Einstein published his theory of general relativity. It changed everything, not just how we think about gravity, but how we understand space and time themselves. And yes, it gets a little strange. But don't worry, we're taking the scenic route. Let's start with a metaphor. Imagine the universe as a giant, stretchy fabric. A bedsheet, if you like. If you place a heavy bowling ball in the center, the fabric dips. Now take a marble and roll it across the sheet. It curves toward the dip, not because the bowling ball pulls it, but because the sheet is curved. The marble is just following the straightest path it can, which happens to be curved. This, in a simplified nutshell, is how Einstein described gravity. Massive objects like planets, stars, and black holes bend the fabric of space-time. Other objects move through that curved space-time. What we feel as gravity is really just the result of us following these curved paths. You're not being pulled to the ground. You're following the natural trajectory of space itself, which happens to dip toward Earth. It's not exactly how Newton saw it. Newton's gravity was a force acting at a distance. Einstein's was geometry. A planet orbits not because the sun pulls it, but because it's riding along a curved path in the fabric of space and time, like a skateboarder in a giant invisible bowl. And yes, it's space and time, not just space. Because in Einstein's world, time is not separate from space. Together, they form a four-dimensional continuum. Space-time. And space-time can bend. That means if gravity is stronger somewhere, time ticks slightly slower there. This isn't theory, it's been measured. The GPS system in your phone has to correct for this effect. Satellites orbiting Earth experience slightly less gravity than people on the ground, so their clocks run just a little faster. Without that correction, your navigation could drift by kilometers every day. Time, as it turns out, is stretchy. Stand on a mountain and your head ages a tiny bit faster than your feet. Not enough to notice. But over long periods, in strong gravitational fields, the difference becomes measurable. Now imagine being near a black hole, an object so massive that it warps space-time to an extreme. As you approach it, time slows down for you relative to someone farther away. To them, you're moving in slow motion. If you got close enough, without being ripped apart, you could experience minutes while years pass for someone outside. This effect is called gravitational time dilation, and it's one of the weirdest, most poetic consequences of general relativity. It also makes for some very dramatic science fiction. The movie Interstellar famously used this concept. 1 hour on a planet near a black hole equaled 7 years elsewhere. That may sound far-fetched, but the math checks out. Einstein's equations have been tested and passed again and again. Light bends around stars. Clocks tick differently in orbit. Space-based experiments like Gravity Probe B have measured the warping and twisting of space-time. Even the recent detection of gravitational waves, ripples in space-time caused by massive objects like merging black holes, has confirmed his predictions. These waves were first detected in 2015, 100 years after Einstein predicted them. They stretch and compress space-time as they pass, like ripples on a pond. But the effect is minuscule, thousands of times smaller than an atom. And yet with instruments like LIGO, scientists measured them. It was like hearing the universe hum for the first time. General relativity doesn't just explain how planets move, it lets us peer into the hearts of stars, the edges of black holes, and the origins of the universe itself. But it's not perfect. As successful as Einstein's theory is, there's one place where it stops working: the quantum world. When you get down to the scale of atoms and particles, general relativity starts to break down. It doesn't play well with quantum mechanics, the other major pillar of modern physics. This has led scientists on a decades-long quest to unify the two, to find a theory of quantum gravity, something that explains how gravity works at the smallest scales. So far, we have ideas: string theory, loop quantum gravity, and others, but no definitive answers. It's like having two perfectly accurate maps, one for cities and one for forests, but not knowing how to draw the trail that connects them. Still, general relativity remains one of the most elegant and accurate theories ever devised. And its core insight, that gravity is geometry, not force, has reshaped how we think about the cosmos. It's not always intuitive. In fact, it's downright weird. But the universe doesn't promise to be intuitive. It only promises to be real. And sometimes real is stranger than we ever imagined. Let's take a moment to reflect on what this means. You, lying comfortably wherever you are sitting on a planet that bends the fabric of space and time. Your weight isn't a force pulling you down. It's the result of you following a curved path in space-time that ends at the floor. The stars above? Each one is curving space-time in its own region. The light from distant galaxies has been shaped by invisible warps in the cosmos. Time itself flows differently depending on where and when you are. And the universe, far from being static, is a shifting, rippling fabric. A vast field of curves and dips and stretches, governed not by invisible strings, but by the geometry of reality itself. Einstein once said, "Reality is merely an illusion, albeit a very persistent one." And maybe gravity is the most persistent illusion of them all. Not a pull, but a path. We're almost at the edge now. In the next chapter, we'll gently step beyond physics and into philosophy, into questions about whether gravity is a fundamental property of nature or something even stranger, an emergent phenomenon, something that might not exist at all until we try to measure it. But that's a deeper mystery. For now, let's rest here, in the curve of a gentle idea, that the universe is not static, not fixed, but subtly bent, and that we, like marbles on a cosmic sheet, are simply following the curves of something far greater than ourselves. We've followed gravity from falling apples to spiraling galaxies, from the feeling of weight on your chest to the very fabric of space-time. We've trusted it, leaned into it, and even reimagined it as geometry, thanks to Einstein. But what if gravity isn't real? Not real in the way we think, at least. What if gravity, that constant presence we've built our universe around, is not a fundamental force at all, but a kind of illusion, a side effect, or an emergent property of something deeper? That's the question physicists and philosophers alike have been whispering for years. And tonight, we'll gently wander into that strange space between hard science and soft speculation. where the rules haven't fully settled and where gravity might be something even stranger than we've imagined. Let's begin with a word: emergence. In science, something is emergent if it arises from the behavior of smaller parts, even though those parts individually don't seem to contain that behavior. Take temperature. A single molecule doesn't have a temperature, but trillions of molecules moving in chaotic motion, that creates what we call heat. It's not a fundamental thing, it's a statistical effect, an emergent property. Now consider gravity. What if gravity, like temperature, is something that emerges, not from a force or even from space-time curvature, but from something deeper, more fundamental? This is the heart of one of the more radical proposals in theoretical physics: entropic gravity. Introduced by physicist Eric Verlinde in 2011, entropic gravity suggests that gravity arises from the thermodynamic tendency of systems to maximize entropy, a measure of disorder or information. In this view, gravity isn't a force or even a geometric effect. It's the result of objects rearranging themselves to maintain the most probable configuration of information in space. It's a bit like watching marbles roll to the bottom of a bowl, not because they're pulled down, but because that's the most stable, statistically likely arrangement. If this sounds abstract, don't worry, it is. This isn't something you'd feel lying in bed or see by tossing a ball, but it could, in theory, explain some of the stranger puzzles of modern physics, especially dark matter. You see, we only see a tiny fraction of the matter in the universe. Galaxies rotate too quickly for their visible mass to hold together. Something unseen, some extra gravity, is at play. We've called this dark matter, but we haven't found it yet, despite decades of searching. Verlinde's theory suggests we might not need to. If gravity is emergent, then maybe our equations are simply off at galactic scales. The extra gravity could be a quirk of how space-time behaves when entropic forces dominate. No particles, no dark matter halos, just a shift in how we understand gravity. Now, entropic gravity is controversial. It's not yet widely accepted. It hasn't replaced general relativity or Newtonian physics. But it's a glimpse, a suggestion that gravity might not be what we think, and it's not alone. Other ideas like holographic principles take this even further. According to the holographic principle, the entire three-dimensional universe we experience might be a kind of projection, a 3D reality encoded on a 2D surface, like a cosmic hologram. This is not science fiction. It's a genuine possibility born from the study of black holes. Black hole thermodynamics revealed something strange. The amount of information, or entropy, that can exist inside a black hole isn't proportional to its volume, but to its surface area. The information about what falls into a black hole may be encoded not within, but on its event horizon. This led physicists like Gerard 't Hooft and Leonard Susskind to propose that maybe everything works that way. Maybe the universe itself is a projection from a more fundamental, two-dimensional reality. And if that's true, then gravity, our good old friend, may just be a side effect of how this projection plays out. Not a force, not a curvature, just the illusion of pull arising from deeper informational rules. It's important to pause here. These aren't facts. They're theories, ideas, possibilities. But they come from real math, from real experiments, and from the very edges of what physics can currently see. And they raise profound questions, not just about gravity, but about what reality actually is. Think of it this way. For centuries, we believed the Earth was flat because it felt flat. Then we discovered it was round. Then we discovered it spins. Then orbits. then spirals through a galaxy that itself moves through an expanding universe. Each step changed our view, not just of physics, but of ourselves. We weren't the center. We weren't standing still. We weren't even tethered to a fixed frame. And now, some scientists are suggesting that even the force that seemed most reliable, gravity itself, may be just another layer in a deeper, more mysterious structure. Something we experience but do not yet truly understand. It's a bit like waking up in a house you've lived in your whole life and realizing the walls may be projections, the floors just patterns, the furniture illusions shaped by rules you can't see. But it doesn't mean you fall through the floor. It doesn't mean gravity stops working. The illusion holds. It's a very useful illusion. GPS still functions. Planets still orbit. Apples still fall. Newton and Einstein are still right, within their own domains. It's just that beyond the horizon, there may be more. So what does all this mean for you, lying there, drifting off to sleep? It means the universe may be deeper, stranger, and more layered than we ever imagined. That what you feel as weight might be the soft pressure of entropy pushing the universe toward equilibrium. That your feet stay on the ground because information prefers it that way. It means science isn't finished. It's never finished. Every answer brings more questions. Every theory is a flashlight in a hallway with more doors. And gravity? It's not just a force. It's an invitation. A mystery that says, look closer, I might be something else. In the final chapter, we'll return to where we began, not floating in space or curled inside black holes, but back on Earth. We'll reflect on what gravity means for our place in the universe, and how something so invisible, so quiet, can hold everything together, including us. And so, we find ourselves back where we started, not in the cold vacuum of space, not drifting past the solar panels of the ISS, or slipping through curved space-time, but somewhere much closer. Home. Back on Earth. Back in your bed, your chair, your quiet nighttime corner, held gently by gravity. When we began this journey, I asked you to imagine yourself floating outside the International Space Station, to picture that strange, beautiful sensation of being free from weight, tumbling softly, watching the Earth roll by beneath your feet. And I asked a few small questions. What is gravity really? What happens when we leave it behind? And what does space teach us about this invisible force that rules us all? After 10 chapters, perhaps the most honest answer is, it teaches us that gravity is far more than we ever imagined, and maybe less than we assumed. We now know that gravity isn't gone in space, it only hides behind motion. That astronauts aren't floating because there's no gravity, but because they're falling perfectly, forever. That inside that orbital cocoon, everything from food to furniture must be redesigned to work without the downward pull we take for granted. We've seen that our bodies too are creatures of gravity. Without it, we swell, we weaken, we stretch. Our sense of direction wobbles. Even our cells become confused. And yet we adapt. With treadmills strapped to the ceiling and toothpaste squeezed from foil pouches, we learn to live without the very thing that shaped us. Then we zoomed out. We saw how gravity creates stars from clouds, sculpts galaxies from light years of emptiness, and binds galaxies into webs that stretch across the universe. We glimpsed black holes, where gravity reigns supreme. We heard the hum of space-time itself as gravitational waves rippled through the void. And then we took a left turn into Einstein's mind, where gravity becomes not a force, but a curve. Where time flows differently depending on where you stand. Where space bends like fabric, and light follows invisible hills and valleys. And still further, We dipped our toes into philosophy, into entropic gravity, holographic universes, and the dizzying idea that maybe gravity is just the shadow of something deeper. That the pull we feel is a whisper from the mathematics of information itself. In every layer of this journey, gravity remained with us, sometimes loud, sometimes silent, always shaping the story. But what have we truly learned? Maybe this: gravity is connection. It's the thing that ties matter to matter, person to planet, planet to star. It's the web that makes together possible in a universe that wants to expand apart. Without gravity, there are no stars, no planets, no structures, no us. Without gravity, the universe would just be a fog of lonely particles. But gravity says no. Come closer, stay together. And that idea, so simple, so powerful, echoes beyond physics. Because when you think about it, gravity is not the only invisible force that holds things together. So does curiosity, so does kindness, so does wonder. It's what brought us here, you and I. Maybe you started this video hoping to fall asleep. Maybe you were simply curious. Maybe you wanted answers, or just something quiet to keep you company as the night crept in. Whatever the reason, you stayed. You drifted with me through black holes and star nurseries, quantum puzzles and coffee-recycled space toilets. You let your mind float, gently, into orbit. And if you're still awake now, hello. I hope your pillow is soft and your thoughts are lighter than when we began. Before we say goodnight, I want to return to the same quiet question I asked at the beginning of this journey. Where in the world are you listening from? And what time is it where you are right now? Are you in New Zealand, where the stars are reversed and the ocean never stops whispering? In Canada, where the forests breathe calmly under snow? Or perhaps somewhere in between, on a couch, in a bunk bed, curled up next to someone who's already fallen asleep? Maybe it's 9:30 p.m. and you're winding down with a warm drink. Maybe it's 2 a.m. and sleep still lingers just out of reach. Or maybe you're listening in the afternoon, your eyes closed, letting science carry you somewhere else for a while. Whatever your time, whatever your place, gravity binds us all. We are held to this planet by the same force that guides the moon, that holds the oceans, that sculpts the stars. And even as we look outward, past Saturn's rings, beyond the spiral arms of our galaxy, we are still part of that same invisible thread. It doesn't matter that we're tiny or that we don't understand everything yet. We're here, we're curious, we're connected. And gravity, whatever it truly is, reminds us of that connection. So tonight, as you breathe in and out, as your body sinks gently into the comfort of home, remember, you are not falling. You are held by gravity, by understanding, by the simple act of caring enough to learn something new. And maybe, just maybe, that's enough. If you've enjoyed this journey, I'd love for you to leave a like and perhaps subscribe to The Sleepy Scientist for more quiet, curious voyages into the cosmos. And if you haven't already, let me know in the comments where you are and what time it was when we began. You never know who else might be drifting off beside you, halfway across the world. Thank you for sharing this time with me. Good night and good gravity.